Right.
So isomorphisms, there's some commentary there, some reading notes, which is kind of like my thoughts on some of the topics. But some of those remarks might make more sense as we go through the chapter afterwards. And yeah, a little section on the exercises and submission problems. Okay, I've given you 4, 9, 12, 47, 55. 55 is somewhat long. Good. But these are for the end of this chapter, so this chapter is timed for 2 weeks. So talking Monday the 20th of November. Okay, so not next Monday, but the Monday after. Okay. And question 55, although it's long, it's like looks like millions of parts to it, but it's a kind of a guided exercise, and it's guided towards quite an interesting result. So what you're basically doing is in question 55, you're going to classify all groups of order 2 times prime. This will be all groups of order 6, all groups of order 10, all groups of order 14, all groups of order 26, everything which is 2 times a prime. Suddenly, when you do this question, you'll completely understand the possibilities for groups of that order. So it's quite a strong result. Okay, isomorphisms. It's a good word. And it's basically, you can think of it in terms of this question. When should we regard 2 different groups as being the same as groups? Now, hopefully you've got an inkling of this kind of idea. So we've seen examples of groups which are groups of permutations of n symbols. These are the elements of the symmetric. We've seen examples of groups which are based on the integers or the real numbers. We've seen examples of groups of matrices, groups of other types of functions, groups of transformations of the plane that have symmetries in certain plane figures. So you can see groups in lots of different mathematical contexts. We think we have seen examples of groups where, so the group D3, the dihedral group, the group of all symmetries of a regular triangle, and the group S3, group of all permutations of 3 objects. They both have 6 elements. And basically, if you label the vertices of a triangle, you can kind of realize any permutation of those 3 labels as some kind of symmetry of the triangle. So when it cycles around, that's a permutation. When it cycles around twice, it's another permutation. And you can also, there are 3 reflections. 2 over here, 3 over here, 1 here. So this is the starting point, and these are all possible endpoints. You can reflect, keep the 3 fixed, swap the others. You can keep the 2 fixed, swap the others. Okay. So these 5 possible ending points, and a 6th ending point where you don't do anything. That gives you 6 elements. Those are the 6 permutations of 3 elements. Okay. So there's a strong sense in which, although these things start out as being different, this is a group, the objects in it are transformations of the plane. The objects in this group are these combinatorial permutations of 3 letters or 3 distinct symbols. But there's a kind of a strong sense in which kind of as a groups, they're kind of should be thought of as being equivalent. Okay. Well, isomorphisms are the way we make this formal and the way we articulate this in group theory. In mathematics is the general notion of structure-preserving maps. Anybody heard that phrase before? Structure-preserving maps. Now you are familiar with this in at least 2 ways, okay? Everybody studied linear algebra last year. So there you looked at linear transformations. A linear transformation T from one vector space to another. Yeah. And the property this has, well, what's a vector space? A vector space is a set where there's the structure of an addition operation and a scalar multiplication. Yeah, there's a vector addition operation and a scalar multiplication operation within a vector space. Now U and V might be two different vector spaces, different elements, some kind of vector addition going on here, some kind of vector addition going on over there. We studied maps from one vector space to another, but not any old maps. Maps which had a particularly nice property, where they preserved the structure, meaning the vector space structure that there was in both sets. And what this meant was that T of a linear combination, alpha times U1 plus beta times U2. So this thing is a linear combination of vectors that takes place inside U. This is the vector addition going on in vector space U. This is scalar multiplication going on inside vector space U. What was this equal to? Remember?
That doing the multiplication of the transformation.
Yeah. So doing the transformation on U1, doing the transformation on U2, and then constructing the linear combination. Yeah. Okay. This linear combination takes place completely in V. This is scalar multiplication inside V because we're taking T of U1, which is an element over here, and T of U2, which is an element over here. So this is the scalar multiplication that's taking place in vector space V. This is the addition that's taking place in the vector space V. So this is one example of a structure preserving map. When you apply the map to the relevant structure, linear transformation, you get the same linear transformation of the mapped elements. Another example is from first year fundamentals, continuous maps, say from the real numbers to the real numbers. You remember the definition of continuity? This preserved, the structure that was preserved here was preserved closeness in a way. So F was continuous at a base point X in R meant for every delta bigger than 0, if X minus A was less than delta, that implied absolute value. No, oops. For every epsilon greater than 0, there existed a delta. F of X minus F of A is less than epsilon. So for every epsilon greater than 0, there existed a delta. You see, this thing is saying X is close to A. X is within a distance delta of A. And this is saying F of X is within a distance epsilon of F of A. So this is talking about being close to A. This is talking about being close to F of A. And a continuous map was one that somehow preserved that notion of closeness. If you were looking for images to be close to a particular image, F of A, then as long as you chose your argument close enough to A, that degree of closeness would be achieved. Okay. So the real numbers with their notion of closeness, which comes from the notion of distance in the real numbers, absolute value of the difference of two things. A continuous map was an example, was a kind of realization of what we mean by a structure preserving map from the real numbers to the real numbers. So we want to see the structure preserving maps in group theory. Okay. Now we're going to see some very special ones today. Okay. So this brings us into definition at the beginning of section 9.1. So we're going to define an isomorphism, or what we mean by an isomorphism. Now, normally up to now, we haven't been including the symbol for the group operation all the time, but we are going to reintroduce it now, just to emphasize the role that the group operation plays. Okay? I'm basically just going to rewrite out the definition here, but just talk about it as we go. So two groups. Now we're going to talk about a group G and a group H, but we're going to reintroduce names for the operations. So G is just a dot operation. H has got circle operation. So two different sets, probably. Two different operations. These are isomorphic. If there is a bijection. Now, what does bijection mean? It's a function phi from one set to the other, okay? Which is bijective, which means it's injective, surjective, or more commonly known as onto one. Injective means one-to-one, surjective means onto. Bijection, okay? Injective, to one, and surjective. Onto, okay? So everything in H gets an element of G mapped to it, and it never happens that an element of H gets two different elements of G mapped to it. Okay? So it's a one-to-one, an exact pairing of elements from G with elements from H. Okay? Yeah. So those are the nicest kind of functions between two sets. You can only have a bijection between two sets that have the same number of elements. So two groups are isomorphic if there is a bijection between them satisfying. Now, what do we want it to satisfy? Okay, you can look at the book and see what the answer is. But what we want this map to satisfy, we're interested in looking at the structure preserving maps. So what is the structure on both sides? Well, in groups, the structure is the operation. So we can dot things in G, and we can circle things in H. And we want the map phi to respect this operation. So that means that if we apply phi to a product, I'll use the same letters he uses, A and B, in G, so this is for all pairs of elements A and B within G, if we choose to apply phi to the element that is the product of A and B, well, what way do we want that to break down? Or what way do we want to be able to re-express this? And it's exactly analogous to the linear transformation property. We want this to be the same as first applying phi to each of the elements separately, and that takes you into the set H, because you've applied phi to A and B. So the value phi of A lives over here, and the value phi of B lives over here. And here the structure is to do with the operation circle. Okay, so if we operate, multiply those two elements together. The linear, if you just focused at the linear transformations and forgot about the scalar multiplication, if you left off the alpha and beta and just saw this as t applied to u1 plus u2, it's equal to t of u1 plus t of u2. Well, that's exactly an example of that. In fact, if you look at a vector space and disregard the scalar multiplication, if you just consider the addition of the vector space, that is a group actually. So you've already been studying group theory when you've been doing vector spaces with that. Okay. So in a way, you should be kind of familiar with this. Now this property has a name sometimes. This is called the homomorphism property. So actually the structure, and it's in a later chapter, the actual family of structure preserving maps are homomorphisms, which are just maps from G to H which have this property. Isomorphisms means the extra condition of bijectivity. Okay? So isomorphisms are special kinds of homomorphisms. A homomorphism is just any map between the two groups that satisfies this property, not necessarily injective and surjective. The ones that are injective and surjective have the special name of isomorphisms. Okay? Okay, so straight away let's look at a couple of examples. So example 9.2. So we'll look at a couple of examples and then look at proving general properties. Okay, let's look at the first example, then we'll close and see if there's any questions we might have. Okay, so the two groups here are R plus and R with multiplication, but of course for that group we need to, well here we're just looking at R plus under multiplication. Okay, so R plus is the strictly positive real numbers. Okay, these are our two groups, and the map we're talking about is the exponential map. Okay, so exp of x is just e to the x, the exponential of x. Well, if you look at the graph of this, the graph of the exponential function looks something like this. That's the axis there at 1, isn't it? And it keeps going asymptotically to 0 as you get larger and larger negative arguments, and it explodes in value, increases exponentially as you get larger and larger positive elements. Sound effects. So we'll take it as a bijection from the graph, so to speak. I mean, to actually prove it's a bijection, you got to get into some stuff about calculus and the real numbers, but the graph looks like a bijection. Yeah. You know, at any particular height, you draw a horizontal line, it cuts the graph in one and only one position. And wherever you draw the horizontal line on the positive across the codomain of positive numbers, it is going to cut the graph somewhere. Even if you draw the line really, really low down, extend it out here long enough, it'll cut it somewhere, because this is converging to 0 asymptotically as x goes to minus infinity. Okay. So we'll take it as read that it's a bijection from all the real numbers to the positive real numbers. Okay. So Salan has this look at me like he's questioning everything I say. It makes me think I'm making mistakes all over the place. But so that's a good note. That's upper quizzical look that you need in mathematics. No, it's good. And what's the homomorphism property here? Well, is when you take the exponential of a sum of two elements here. Well, the group operation here is plus. So here we're talking about x plus y. Taking the exponential of it, yeah. The right-hand side of the homomorphism property would be separately applying the map to the two elements and then doing the operation. So separately applying the map means looking at e to the x and e to the y, the exponential of x, the exponential of y. Then afterwards doing the operation. But in the other group, the operation is multiplication. So it's just plain multiplication of those two. Are those two equal? Yeah, that's just our well-known, familiar property of exponentials. The well-known property of exponentials. So this thing we already knew about, and it's not just true for e, it's true for an exponential with any base, not just the natural. E is the base of the exponential. This is just a general property about how indices work with addition and multiplication of real numbers. Okay, so this is something we already knew about, so it is an example of an isomorphism. Okay, so this group, the real numbers under addition, although it's completely different to the positive real numbers under multiplication, okay, they're different sets. Okay, this one contains that set, but so they're different sets. They're very different operations. Addition of numbers is not the same as multiplication. But the group structure that there is, in addition of real numbers, is somehow equivalent or should or can be thought of as being the same as the group structure that there is with the multiplication of positive real numbers. Because there's a way of mapping one set bijectively to the other set using the exponential function. And the exponential function interacts perfectly with the two group operations in this homomorphism property way. Okay? So a product of elements in one group gets mapped across to the product of the corresponding images in the other group. Okay? Let's go back to example 9.1. I skipped example 9.1. So that's an infinite example where the groups are infinite. Example 9.1. So on the one hand, we've got the group Z4, which is the integers under addition mod 4. Okay, you're well familiar with this from your number theory last year. So you represent the congruence classes using the integers 0 through 3. And the operation is the sum of elements modulo 4. Now there's only 4 elements, so I can quickly draw the 4x4 Cayley table, even though it has 16 elements. Okay, so it's completely everything going on in that group. Okay, take 2 elements, add them. 2, 3, good, except that way. 0, 1. So I should say 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0. Okay, so that's the group Z4 under addition. Mod 4. The other group is the subgroup of, compare this to subgroup of C star, so the non-zero complex numbers under multiplication, generated by I, the imaginary unit. Okay. What kind of things can you generate from I? I to the 0 is 1. I to the 1 is 1. I squared is minus 1. I cubed is minus I. If you look at further powers, you just repeat those elements. Okay? So those are all the powers under this operation, multiplication of the complex unit of the imaginary number I. We can quickly draw its Cayley table. I cubed minus I. Yeah. Minus I. 1. I minus 1. What can we see there? Looking at those two Cayley tables.
Like an onto mapping.
Huh?
Like an onto mapping.
Yeah, or just what's going on with those two Cayley tables? Is there some way you can just wrap up the whole discussion?
Oh, is it powers of I? So obviously.
Yeah, it's powers of I, because we're using the operation of multiplication here. I mean, it's powers of I here, but understood additively. Powers of 1 here, 1 squared additively is 1 plus 1.
Could you just relabel one as the other?
Yeah. Really, so yeah, this table, the two tables are just relabelings of one another. if you relabel the elements 0, 1, 2, 3 with the elements 1i minus I minus 1 minus I, if you make that association, then you got to relabel the body of the table under that association well, and then the two labels just become the same. Supposing there was an alien civilization who understood about adding integers mod 4, and they understood about multiplying complex numbers, right? They developed, they've never met us before. They know nothing of our writing system or our English. They suddenly landed here, came in here, they got the vibe we were doing group theory. They look at the board and say, oh yeah, there's 4 element groups going on. What groups are they talking about? Would they be able to distinguish these two? And they know nothing of the English language or what particular any symbols we use. They would recognize, they could have said, oh, this must be Z4. Look, this is the thing we call 0 here. This is the thing we call 1. This is the thing we call 2. This is the thing we call 3. They've got weird symbols for them. But everything would check out. This is the table of Z4. If by this you mean 0, and this you mean 1, this you mean 2, and this you mean 3. Everything else works out. Or equally well, they could have looked at that and thought, yeah, that must be 1. That's their symbol for 1. That's their symbol for the imaginary number. That's their symbol for minus 1. Right? The two just are exactly relabelings of each other. Okay? And that's your bijection. So there's obviously loads of bijections because they're both 4 element sets. Okay? So there is a bijection. There is a bijection phi from Z4 to the cyclic subgroup generated by I. I mean, there's no formula for it as such, but 0 maps to 1, 1 maps to I, 2 maps to minus 1, and 3 maps to minus I. That's the bijection. And the fact that the tables are just relabelings of each other means that, see, when you apply phi to 3, 3 you can think of as 2 plus 1. So phi of 3, what you see over here in position phi of 2 multiplied by phi of 1, what do we see? Well, we see minus 1, which is phi of 3. Yeah? And the fact that the bodies of the tables, everybody clear on the term body of the table? So the body of the table is that bit in the middle. You've got the row and column headings in the body of the table. Body of the table. And the fact the bodies of the table, what's the word? Are identical under this map, are, what am I trying to say? The bodies of the table also map across under phi. So phi, if you just apply phi to this body, you see it over here. That is, in effect, that is the homomorphism property. Because what you're seeing in the body of a table over here is A plus B. That's what's in the body of the table over here. But what's in the table of the body over here is phi of A plus B. But because everything maps across consistently, the thing at position phi of A plus B over here will be phi of A, the row element, multiplied by phi of B, the corresponding column. Okay. So again, those groups are isomorphic. The integers under addition mod 4 and the complex numbers that are generated from the imaginary number of I. Example 9.3 on page 156 just talks about exponentials to a different base 2. It's time to rational numbers, but it's all It's all good. It's all the same. And yeah, then a couple of negative examples. Example 9. So, it's good to see positive examples and negative ones. So, for instance, Z8 and Z12, they cannot be isomorphic because they fail the first test. They just got different numbers of elements. Okay, there's 8 things in Z8, there's 12 things in Z12. So you can't have a bijection between them. Okay. However, it does remark that if you look at U8 and U12, so remember these are the groups of these under multiplication modulo 8 and modulo 12. Remember, they only consist of the things from Z8 that are coprime to 8. And that's just 1, 3, 5, and 7. And the things from Z12 that are coprime to 12. So it's only 1, 5, 7, and 11. But there is so these have a chance of being isomorphic because they're both 4-element sets. And indeed, there is a mapping between them. Well, so there will be lots of bijections from this set to this set. The question is, are any of them homomorphisms? Do any of them respect the group structure? Well, you can discover one. It does happen to be the way they're laid out there. So sending 1 to 1, 3 to 5, 5 to 7, and 7 to 11. If you check, well, one way to check is to do the multiplication table for them both, do the KD table for them both. See that under this relabeling, this will relabel the KD table for U8 and it will become the correct KD table for U12 if you relabel the body of the table using this association. Yeah,
is it just that it's coincidence that the U8 and U12 are both a prime plus 1 in link to each other? For example, it's 7 and 11. So would that work for, let's say, 12 and 14?
Tell me. Does it work? Beautiful question. U14, what are the elements of U14? So everything coprime to 14. Everything from Z14 that's coprime to 14.
So it's
so no
under addition.
No, this is the group under multiplication.
Right.
That's why we're chucking out everything. We're only keeping those things coprime to the modulus because they're the only ones that have multiplicative inverses to the modulus. Be ingrained into your mind.
I was going to say,
number theory.
So I was trying to revert back to number theory.
So things coprime to 14. So this is everything from Z14 except the multiples of 2 and the multiples of 7.
Yeah. So
1, 3, 5, not 7.
No.
9, 11, 13.
Right.
So can that be isomorphic to?
Well, no, because it's got 6 elements.
No, it's got more elements.
Right.
Okay. That's cool. You formed a conjecture and you disproved it.
Yeah.
Yeah, it's great. A way to understand why it is, a nice way to understand why it is, well, okay, we'll leave that. Let's just take it. So if you draw out the multiplication of the table list, relabel it under this association, and it will become the correct Kelly table. Here's an interesting example, which is linked to a general 9.5. S3 and Z6. Remember, S3 is all permutations of 3 objects. There are n factorial of those, so there are 3 factorial. So there's 6 permutations of 3 objects. Z6, the integers under addition, modulo 6. 6 objects, 0, 1, 2, 3, 4, 5. Okay. Are these groups isomorphic? There are loads of bijections between them, because they're both 6-element sets. Now, so if they were isomorphic, what we're kind of saying is they should be regarded as being the same as groups. There's one clear way where these have very different group properties. That's the fact that Z6 is abelian. S3 is, yeah. So addition of integers, even though they're addition modulo 6, but a plus b is always the same as b plus a. Doesn't matter the order. But the operation here is function composition, which in general is not commutative. It makes a difference in which order operations are performed. So we shouldn't feel that they should be regarded as being equivalent as groups. And indeed, that property of being different commutative status means they can be. So you can prove that. So it's a proof by contradiction. So suppose that we did have phi an isomorphism from one set to the other. Suppose there was. Then you'd let A and B be two elements of S3, which is the codomain of phi. So because phi is a bijection, A must have come from an M, so phi of M equals A. B must have come from a M. So M and N are elements of Z6 that get mapped to A and B. Okay. And what we end up doing with appropriate application of the homomorphism property is just look beginning to end. We somehow prove that A times B is equal to B times A. And this is within S3. Now that's true for some pairs of elements in S3, but it's not true in general. Okay? Because composition of permutations is in general not commutative. So you shouldn't be able to prove that AB equals BA. Now how do they prove it? Well, AB, by definition, is phi of M times phi of N. But by the homomorphism property, if there was this isomorphism phi, instead of multiplying phi of M by phi of N, which takes place in S3, we can instead apply phi to the sum of M plus N in Z6. Okay? It's the homomorphism property that says that those two are equal. So in a way, you pull back the product AB, you pull it back into a product within Z6. You can then make use of the commutative nature of the operation in Z6 to flip it around. You then apply the homomorphism property again, so you're pushing it back into S3, pushing the product operation back so that it takes place in S3. And then suddenly you seem to be looking at the B times A. Okay? So assuming they are isomorphic, you can show that S3 is abelian. But we already know it's not abelian. So therefore, proof by contradiction, they can't be isomorphic. So that's a good example. That's our first proper negative example of two groups which have the same size. They're both 6-element groups. And we already kind of feel that they shouldn't be isomorphic. They shouldn't be considered the same as groups. Different commutativity status, different abelian status. And indeed, we can build a proof by contradiction that they're not by making use of that abelian status. Simultaneously, what we're looking at there can be interpreted positively as saying that if two groups are isomorphic, and you know that the first one is abelian, then this is the argument that proves the second one must also be abelian. Because that's effectively what we did. We used the abelian nature of Z6, which took place here. This is the abelianness of Z6, to prove that the operation in the codomain is also commutative. So that argument generalizes to anywhere where phi is an isomorphism from one group to the other. So if two groups are isomorphisms, so that's property 3 in the next here. If phi is an isomorphism from a group G to group H, then if G is abelian, then H is abelian also. So in theorem 9.6, which moves us neatly onto that, this is our first look at lots of group properties that are preserved by isomorphisms. Remember, we introduced it by saying we wanted to capture the idea of when groups should be regarded as being the same. So these are examples of if phi is an isomorphism from G to H. If you look at H, if you look at G with group theory, glasses, when you put on glasses, you only see group theory stuff in G. When you look at H, it looks exactly the same, in a way, that's what it's saying. So the H will be isomorphic to G as well, that's the first thing. Strictly speaking, as we've defined it, it's a kind of a directional relation. G is isomorphic to H. The first thing is isomorphic to the second. Well, the first property says, well, it goes the other way as well. G is isomorphic to H is isomorphic to G. The orders are the same? Well, that's just because there's a bijection between the two sets, isn't it? This argument we just saw here proves if the first one is abelian, so must the second one be. So if that looks abelian, well, that one's abelian too. If the first one is cyclic, well, so is the cyclic. Basically, any property that's articulated in group theory terms, if it's an isomorphism, H should look exactly the same. So if G has within it a subgroup of some size, you'll also find a subgroup of that size inside H. Basically, any group theory in G will be the same as H. And that all flows from the homomorphism property. Because this is all there is to a group is the operation. So if you've got a bijection, an exact mapping of the elements from one to the other, and the operation is respected by that mapping, then anything groupy that goes on in G will be the same in H, basically. So, I mean, we've proved some bits of that just in what we said. Maybe the cyclic needs a bit of an argument, the existence of a subgroup needs a bit of an argument. But we can look at that tomorrow. I mean, you can read about it. I think he defers most of those to exercises. Okay, we better stop there. It's 10 to 5. Okay.